Paper on thermodynamic topology of topological charged diatonic black holes explores the thermodynamic topology of charged diatonic black holes within the framework of dilation gravity. The study examines how the topological constant affects the event horizon of these black holes and evaluates their thermodynamic and conserved quantities. To confirm the validity of the first law of thermodynamics, by considering black holes as thermodynamic defects, the authors analyzed their local and global topology using thermodynamic ensembles. First is fixed charge ensemble and second is fixed potential ensemble. The paper examines how the topological charge of black hole is influenced by the dilation gravity parameters and the topological constant. The authors identified different topological classes of black holes based on their thermodynamic behaviors. The analysis is performed for three types of curvature hypersurfaces. First is elliptic, then next is hyperbolic, and then flat. The topological constant of elliptic is positive 1, the hyperbolic is negative 1, and the flat is 0. The conclusion part, the topological charged diatonic black holes do not exhibit asymptotic flatness or Hodge behavior due to its dilation field. Lastly, the topological charge and phase transitions depends on the parameters such as topological constant, dilation coupling, and cosmological constant. The paper on a mathematical theory of running based on the first law of thermodynamics and its application to the performance of world-class athletes presents a new mathematical model for analyzing running performance. It is based on energy considerations, specifically the first law of thermodynamics, and avoids using mechanical efficiency factors, which were common in the previous models. The analysis provides a relationship between race, distance, and time, successfully correlating with data from Olympic Games performance 100 meters to 10,000 meters races. According to the paper, existing models relied on Newton's second law of motion but had physical limitations. The paper then proposes a thermodynamic approach to running, considering all forms of energy exchanges in the body. Then it aims to predict and analyze the velocity-time relationship for sprinting and long-distance events. Key findings of the paper in terms of energy balance in running. The chemical energy released by the body is converted into mechanical work and heat. The model then properly accounts for all energy terms, avoiding arbitrary efficiency factors. Next is velocity-time relationship in sprints. The peak speed is achieved around the middle of 100-meter race. After reaching its peak velocity, runners experience a slight deceleration, which previous models failed to predict. This is sprint versus long-distance running. Sprinters use maximum power throughout the race, while the distance runners maintain an even pace to optimize energy use.